Okay, let's dive right into this explainer. If you're gearing up for your first semester data analytics final, you are in the exact right place. We're going to take all 12 weeks of your handwritten notes and synthesize them into one high-yield study session. Look, I know exactly how it feels to reach the end of the term, open up your notebook, and just see a massive wall of information. But don't worry, we're breaking it all down logically so you can walk into that exam room feeling absolutely confident. Seriously, if you are staring at a mountain of definitions, pipelines, and formulas right now, take a deep breath. Please don't panic. Instead of trying to memorize a bunch of disconnected facts, we're going to tackle this by following the natural life cycle of data. When you organize your studying around how data actually moves and evolves in the real world, I promise you these concepts will lock into your memory so much faster. So here is our roadmap for today. We're going to hit the data analytics lifecycle, where data lives, privacy and ethics, cleaning and transforming, combining data, and finally, visualizing the results. Let's get to it.
All right, part 1, the data analytics lifecycle.
A classic test question always asks about the end goal of all this work, and it follows a very specific progression of understanding. If there's literally one thing you remember for the exam, make it this list. As analysts, we always start with exploratory analytics. That's just gathering and figuring out what the heck we're looking at. Then we move to descriptive analytics to answer, okay, what happened in the past? Once we know that, we use diagnostic analytics to ask, well, why did it happen? But we don't stop there, right? We take that historical insight and use predictive analytics to forecast what could happen next. And finally, the holy grail for businesses is prescriptive analytics, which tells decision makers, here is what we should actually do about it. Nail that progression, and that's an easy point on your test.
Moving right along to section 2, where does data live? Before we can analyze a single thing, we have to pull it from storage. And your notes have a brilliant set of analogies here that are basically a cheat code for exam recall. Think about how you store food in your kitchen. A database, that's your small fridge. It's highly organized, meant for everyday, lightning-quick access, like grabbing a single customer's order. A data warehouse is more like a large pantry. It uses processes like extract, transform, load, or ETL to neatly organize bulk data for multi-purpose reporting. And finally, a data lake is a massive reservoir. It doesn't force data into a neat structure, it just holds a vast amount of raw, unstructured data in its native format. Honestly, it sometimes acts more like a data swamp, but it's ready for whatever advanced predictive modeling we might want to throw at it later. And speaking of storage, you are practically guaranteed to see a question comparing databases on your final. The crucial difference is structure. Relational databases use SQL. They are rigid, structured perfectly in rows and columns, and they minimize data redundancy. On the flip side, non-relational databases, often called NoSQL, are incredibly flexible. They're schema-free and built specifically to handle massive, messy, unstructured big data like endless social media feeds.
All right, part 3, data privacy and ethics.
Because data belongs to real, actual people, protecting it is a crucial step before we even think about cleaning it. Lock this exact definition into your brain for the exam. Personally identifiable information, or PII, is unique identifier data. We're talking full names, phone numbers, email addresses, or government IDs like an Aadhaar card. If this specific stuff is leaked, it severely breaches fundamental privacy principles and destroys consumer trust. So how do we actually use data safely? We use data anonymization. This is how we analyze big trends without spying on individuals. Anonymization involves taking that PII out completely or using techniques like generalization. For instance, you'd swap out an exact date of birth for a generalized age range, like 20 to 25. It preserves the usefulness of the data for our analysis without sacrificing the privacy of the person behind it.
Section 4, cleaning and transforming data.
Now that we've ethically sourced our data, it's time to get it ready for analysis, which means building pipelines and scrubbing out errors. The foundational movement of data relies on the ETL pipeline. Mark my words, this will be on the test. Step 1, extract the raw data from wherever it currently lives. Step 2, transform it. This is where the heavy lifting happens, removing duplicates, fixing weird date formats, standardizing units. And step 3, load that newly polished, analysis-ready data into its final destination, like a data warehouse, so the business can actually use it. Let's dig a little deeper into that transform phase. When it comes to the nitty-gritty of cleaning data, just remember this 3-step sequence. First, you inspect to find missing values or formatting errors. Next, you clean the data to fix those discrepancies, maybe by dropping nulls or correcting typos. And finally, and listen, students always forget this one, you must do verification. You have to document all the changes you made and verify that your fixes didn't accidentally break something else. For the math section of the exam, you'll need to know about z-score normalization. We use this for standardizing data when variables have vastly different units of measurement. The formula is straightforward. You just take a value, subtract the sample mean, and divide it by the standard deviation. It beautifully scales your data so that massive numbers don't unfairly dominate your entire analysis.
And right next to that in your notes is min-max scaling, also known as normalization. This technique rescales your data to a fixed exact range, usually between 0 and 1. But here is a massive red flag for your exam. You have to be super cautious when using min-max scaling because it is highly sensitive to outliers. Since the formula uses the absolute minimum and maximum values in your dataset, just one giant outlier will skew your entire scale.
Section 5. Combining and structuring data. After transforming single datasets, an analyst has to connect different tables together to find the real insights. Because let's face it, you rarely have all the answers in just one spreadsheet. To do this, you must understand your keys. The primary key is your unique ID for a specific row. Think of a student ID number. A compound key is when you need to combine two columns to make that unique identifier. And the foreign key? That acts as the bridge. It's a column in one table that references the primary key in another table, allowing you to seamlessly link them together. Take a mental snapshot here because you are definitely going to need to explain how SQL joins handle overlapping data on your final. Let's make it simple. Inner join gives you the intersection, only the exact matches. Left join gives you everything from your first table, plus whatever happens to match from the second. Right join is just the reverse of that. Full join grabs literally everything from both matches or not. And union is a bit different. Instead of combining columns side by side, it vertically stacks tables on top of each other as long as they have the same columns. Memorize that logic. And finally, Section 6, visualizing the final results. All that hard work, the extracting, the cleaning, the joining, it means absolutely nothing if we can't present our findings clearly to decision makers. A huge concept to know here is Anscombe's quartet. It brilliantly illustrates why you cannot just rely on summary statistics. It refers to 4 distinct datasets that share almost identical stats, the same mean, same variance, same correlation. But the second you graph them, they look completely wildly different. Anscombe's quartet proves that visualizing your data is absolutely mandatory to uncover the real relationships hidden in the numbers. But a proper visualization doesn't just look pretty. It relies on strict aesthetics. You need an informative title so people instantly know what they're looking at. You need clearly labeled axes that explicitly state the unit of measurement. You need a useful legend. And crucially, you need 0 unnecessary visual clutter. Seriously, don't just throw 10 colors on a bar chart for fun. And please, no 3D pie charts. Good design guides the viewer effortlessly straight to the insight. Well, that wraps up our review. If you study these core steps, from data collection all the way to visualization, you are going to absolutely crush your first semester exam. But honestly, more importantly than that, you're learning how to translate raw noise into actual truth. Once you master this life cycle, the question isn't just about passing a test anymore. It's asking yourself, what story are you going to tell with data next?